next topic is the network layer, so layer 3. Job of the network layer is to find a reliable path from source to destination. Remember, it's link layer that creates the reliable path, and the network layer has to stitch together these paths to find the source, to find a path from source to destination. We're going to see that you can do this, perform this action, either in a centralized way, right? Meaning a central entity can do it, or it can be done in a distributed way. So these are the two types of routing algorithms that we're going to talk about: centralized and distributed. Also, there's a variety of other functions that are implemented at transport layer that are related to finding this path. For example, you need to address interfaces and so on. So addressing is done at the network layer. This is the so-called IP address. Okay, so we'll talk about these and a bunch of other functions, right? So here's the outline. Let's just get right into it. Okay, so the network layer gives you a logical connection between two network interfaces, right? So for example, you have, so you've seen this diagram before. You have the devices on the edge that implement all the way up to application layer. But from that point on, the core routers in the internet and so on only implement up to the network layer. Okay, so you have this packet that is going to sort of go up and down the stack, and in the core routers, it's only going to be processed up to network layer. Okay, and which tells you that what these intermediate nodes have to do is they have to read the packet, they have to look at what is the destination, and they have to forward the packet accordingly, depending on what is the destination. Okay, so the core function that a router carries out, right, is forwarding and routing. Okay, so forwarding is the act of taking an incoming packet and deciding which output interface to transmit the packet on. That's forwarding. Okay, routing is deciding what is the next hop node. Right, and of course these two are related, right? The routing algorithm will drive the forwarding algorithm. Okay, so we just break it up into these two. Like initially we like to say, oh, the job of the network layer is routing, right? But actually there's two, it's a subtle point, but there's two functions that are going on here. Okay? So I think I have an example here. So here is the interplay between routing and forwarding, right? So this is an example of a small network. It's a 6-node network. The edges here represent connections between the nodes. Okay, so I'm specifically looking at this router here. Okay, and this router has a forwarding table, and that forwarding table looks like this. It's a table. One column of the table are the set of all possible destinations. The second column is if a packet with that destination comes in. The second column tells you what interface that destination is available on. Okay? So for example, suppose a packet comes in and the destination is 0111. So if you look at this table here, 0111, we see we should forward on interface 2. And so that's what these labels are, just the enumeration of the interfaces. So because 011 is 2, the router will forward on interface 2. Okay? Now the question is, what determined this forwarding table? That's the routing algorithm. Okay, so that's the interplay between routing and forwarding. Okay, so we've already talked about, when we talked about internetworking, we talked about circuit switching versus packet switching. So this idea also shows up here at the network layer, okay? Because depending on what you're using, circuit switching or packet switching, the network layer has to act accordingly. So when you're doing packet switching, we have what's called a virtual circuit network. Essentially, it's just the idea of packet switching. So it's just the idea of circuit switching, right? In circuit switching, if you remember, you have to reserve resources along the end-to-end path. In packet switching, you don't. It's on-demand allocation of resources. And the packet switch network, because the object at the network layer is called a datagram, it's called a datagram network. Okay, so in a datagram network, there's no call setup. Now, transport layer, which is end-to-end, has a call setup. Network layer has no call setup. Okay, so when we say transport layer has call setup and network layer doesn't, what that means is that the functions running at the network layer don't do setup. And the functions at transport layer, like TCP, does call setup. That's what we mean when we say that the network layer has no call setup. Okay, so the routers, they don't do end-to-end. Okay, now it may be that a router may need to know about network topology in order to do routing. So it may have that type of information. But what it doesn't have is information about the state of the network. Okay, it doesn't know, for example, if routers are full or what their link rates are or so on. Okay, and packets are forwarded using the destination host address. Now, since routing is so I mentioned to you the routing algorithm drives the forwarding table, and because the network is dynamic, the routing algorithm may change routes, right? May change the forwarding table. So packets are not guaranteed to take the same path from source to the destination. In fact, the network layer, as it is, provides no guarantees. Okay, it doesn't guarantee bandwidth, it doesn't guarantee delivery, it doesn't guarantee anything. Okay, so here's an example of a forwarding table in a real router. So the addressing scheme used at the network layer is the IP address, and IP addresses are 32 bits. So I told you that the forwarding table contains all possible destinations. So how many possible destinations are there if I have a 32-bit IP address? Yeah, this is a question for you. Yeah? Yeah, 2 to the power 32, which is about, what did I say? It's about 4 billion. So in theory, the forwarding table should have 4 billion entries. Every forwarding table should have 4 billion entries. And that really would need to be the case if we couldn't exploit some sort of structure. And what happens is the network layer, the IP addresses have a structure. Okay? The structure, and I think in homework 1, you had to go think about that structure, right? So anyone can remind me, what's the structure of IP addresses at the network layer? Yeah, anybody know? How are IP addresses structured? They're 32 bits, but beyond that, there's a structure. It also came up when we talked about why do we have MAC and IP addresses, right? That question came up. So it's important to make connections between things. Learning is not linear. It's not like, Prof, we never talked about that, so therefore, I need not know it. Actually, you should know it because you encountered it 2 times already. Okay, Benita, you said hierarchical. What does that mean? Can you elaborate? Yeah. Okay, yeah. Good. So some good ideas there. A bit simpler. Can anybody give me a simpler explanation? Well, network interfaces that are geographically close have similar addresses, right? Just like the postal system. If you live in Clementi area, probably your postal code starts with a 1, right? On campus, it's like 1, what? Anybody live on campus? What's your postal code? Yeah, anybody know the postal code on, like, for if you live in PGP? And anybody here live near campus? What's your postal code? 1? Okay, 138. Yeah, anyone else live closer to campus? I can guess you don't live super close to campus. Oh, it's Newtown. Oh, okay, it's 138. I didn't know that. Yeah. Well, a lot of this area is 1 something, but Newtown is 1 something. So, but you'll see that all this area will be 1 something. Okay, so IP addresses are handed out in a similar manner. Devices that are, or interfaces that are geographically co-located. Yeah, and so what this means is you can exploit this structure. So as Benita said, if you want to route to a node in Singapore, you just need to know, for example, what's the common thing about IP addresses in Singapore. One of the things you'll find is that it's 137 dot something represents a Singapore address. So that means that nodes outside of Singapore only need to remember 137 dot. So that already reduces their forwarding table by what? So 137, let's say, is 8 bits, so there's 24 other bits. So it needs, right, it needs to have that many less IP addresses, 2 to the 24 less IP addresses in its forwarding table. So what I've shown here is, like, shown you 4 entries, and each entry represents a range of addresses. Okay, so you can see the first range, here I'm just showing you all 32 bits. But if you look at the first entry, what can you tell me about the first entry? All the addresses in the first entry, that's a range of addresses, what's common about them all? The first what? The first 2 bytes, is that it? So the first 16 bits, yes. What else? Is that it? How about the next 4 bits? And how about the fifth? So that's 16, 17, 18, 19, 20, 21. We see the first 21 bits are the same, right? And you'll find the same thing in all the other ranges, okay? And then there's a catch-all otherwise. Okay? So this is what forwarding tables in routers look like. Now, because the first entry, the first 21 bits are the same, in fact, that's all I need to remember, the first 21 bits. So, I mean, I drew it like this. I mean, I listed it to show you the range, but actually the entry would just be the first 21 bits. We call that the prefix. Okay, so how is routing done? Routing is done by doing longest prefix. Sorry, how is forwarding done? It's done by doing longest prefix matching. So what a router will do is it will take the incoming address and it will match the prefix. Right? But you can have nested ranges of IP addresses. So what I know, it can have multiple matches. So it's going to match the longest prefix. So for example, this is the forwarding table that was on the previous slide. This is what it would really look like. Right? So notice actually that prefix entries 2 and 3, actually they overlap. Okay? So here's an example. If the destination address looks like this first one here, right? So we basically do longest prefix matching. So which interface would this be routed on? Yeah, you just look at this and figure it out. Which is for this IP address, which is the longest prefix match? You know? Sorry? Interface 0. Why? Yeah, a bit louder. Yeah. Yeah, that's right, because these are 0011, right? So this is 0010, and that matches it. So this would be to interface 0. Okay? How about this one? Which one does this match? Remember, we're doing longest prefix matching. Okay, so someone said 2. So it does match, right? 0011. That's correct. 2 is a match. Is it the longest match? So what interface will this forward on? What interface will this packet be forwarded on? Right, because you can see that the first 24 bits match here, right? This is 00011000. Right, so this will get forward on packet 1, on interface 1. Okay, so yeah, so I hope you have an idea now how this idea of hierarchical addresses helps us do routing in a scalable manner, or do forwarding in a scalable manner. Otherwise, you'd have to search, right? You'd have to have a bunch of IP addresses, and you'd have to search for it. And search takes roughly, well, sorting takes n log n, right? Search is roughly log n. So it increases as the size of your forwarding table increases. So that complexity is too much for routers to be able to do very, very fast routing. So here, the forwarding tables can be much, much smaller. Okay, so I think this issue of circuit switching versus packet switching is the same. I mean, the pros and cons are the same as we discussed during internetworking. If you want to have guaranteed services, you need to do circuit switching. If you want to exploit efficiency, if you want to get efficiency by exploiting the fact that resources are not used all the time, then you do packet packet switching, and essentially all modern networks do packet switching. Okay, they're datagram networks. Okay, so any questions? So that was just kind of an overview of what routers do, a little bit about how they do it. We're going to talk a lot more about IP addressing and about routing. We'll talk a little bit about forwarding now, but not too much, because the issue of forwarding comes down to switch design. There's a switching fabric between the input and output of a router, and the design of that is the forwarding algorithm. And it turns out that's a very deep area of research, so we'll touch upon it briefly. Okay, so let's look at what's inside a router. So a router has input ports, has output ports, and it has something that connects the input and output ports, which is the switching fabric. Then there's a CPU or some sort of processing component. This is where the routing algorithm runs. Okay, so and then there's a memory where the forwarding table lives, right? And the routing algorithm determines the forwarding table. Okay, so let's talk a little bit about each of these. Okay, so the input port essentially implements the physical and link layer. Okay, and these are typically implemented in hardware, right? You have a physical device, right? Either if it's wireless, then, well, it's on the wireless chip, which is sometimes integrated with the CPU. But if you're doing Ethernet, then there's this port, right, that you connect the cable to. Right there's a little piece of hardware inside your computer that's doing this. Okay, the physical layer and the link layer. So the line termination is part of the physical layer. This next block here, this is the link layer. Okay, then after the packets are processed through these two blocks here, they go into a queue. Okay, well, they are waiting to be forwarded on the switching fabric, right? Because the switching fabric has a certain performance, and it could be that data comes in faster than the switch can forward. So that's why you need this queue here. Okay? So maybe I pause on this for a minute and just show you the output port. So the output port is on the other side of the switching fabric. And the output port just implements, so the output port also has a queue, okay? And then the output port implements the link layer and the physical layer, okay? And then it transmits the packet. Now, this transmission, this link rate here could be slower than the switching fabric. And that's why you need this queue here. Okay, so there's the input port queue, and there's the output port queue. And then between those is the switching fabric. So let's talk about the switching fabric. There's broadly 3 types of switching fabrics, and they were developed chronologically, right? So older routers would have the older types of switching fabric. So we can switch via memory, can switch via a bus, you switch via a crossbar switch, or essentially it's like a crossbar bus, okay? So switching via memory is pretty straightforward. There's some common memory location that it writes to, and then the CPU directs the output. So the CPU directs the input port to write to some memory, and then it directs the output port to read from that memory location. This works well. It's conceptually easy, but if you ever work with computers, you know that reading and writing memory is very slow. So this is very slow. Okay, so the first generation of routers had this. Switching via bus essentially is there's a shared wire that both the input and output port can stimulate and sense. Stimulate would mean writing, sense would mean reading. Right? So then the CPU would, again, on this shared bus, would instruct the input and output ports to do the necessary actions. Now, so I'm showing you an example here of 3 input ports, A, B, C, and 3 output ports, X, Y, Z. And we can see that if input port A is trying to forward to output port Y, well, then none of the other ports can transmit. So even if, like, for example, X and Z, so in this case, actually, Z is not being used. What if C wanted to send to Z? It's not possible here. Right? It's just like Ethernet. Remember, Ethernet is a shared medium, right? So when one node, before a node transmits on Ethernet, what does it do? Do you remember from the first part of class? What does a node do before it sends its packet on the Ethernet? Sorry? Yeah, why does it sense a line? Yeah, it's trying to see if someone else is transmitting, right? If someone is transmitting, it's not going to transmit. Same thing has to happen here, except here it's not random access, right? The CPU, the routing processor, is instructing. But because it's a shared bus, simultaneous transmissions cannot happen. Okay? So this is like the, but this is much faster than via memory. So the second generation of Cisco routers use this. Now, the crossbar switch is very similar to this, except we want to allow, in this type of situation, C to send to Z. Okay? So what we do is we still have like shared buses, but we allow for lines to be connected and disconnected. So for example, in this, if A wants to send to Y, I think that was the example here, right? A is sending to Y. So if A wants to send to Y, then these connections are kind of turned on. So this path is active. But C can also send to X. Now, maybe B cannot send to Z, right? Because that crosses this path here. But I can still allow C to send to X by closing this connection. Okay, so this roughly doubles your the number of connections and doubles the rate. Right? So modern Cisco routers use this kind of switching fabric. Right? So you roughly go from 32 gigabit per second to 60 gigabit per second. Are we good? So as I said, this is really a big area of research, because if you can make switches, the switching fabric switch faster, you can make routers work faster. So this is a huge area of research. Right? So we just touched the tip of the iceberg. Okay, so we already saw the output port. Now, remember, both the input port and output port have buffers and queues. So this is actually where packets can get lost. Right? If the input port buffer fills up before the switching fabric empties it, packets can get dropped. The same thing with the output port. If the output port fills up before the transmissions, the node is finished transmitting, packets can be lost. Okay, but to show you why this is a big area of research, we'll look at so there's obviously output port queuing, right? Which is that whenever there's contention for a specific port, right? Only one of the nodes is going to win. The other nodes have to wait, right? So you're going to get competition for the output port. But what's more interesting is input port queuing, because this this we can kind of predict. This is what we expect to happen. But this is something that's kind of new. You can have queuing at the input port due to strange things like head-of-line blocking. So for example, so here I have 3 input ports and 3 output ports. And let's say that both, so I think this was what, ABC before? This is X. Right? So let's say that A and C both want to send to output port X. And so suppose that all red packets are meant to go to output port X, and green packets are meant to go to output port Y. Now, if A and C are going to compete for output port X, well, one of them will win it. Right? Now, in this case, is it really a competition? I'm not sure, because I told you the routing processor does it. But the routing processor has to make a decision, right? A or C. Okay? Now, if A gets that use of output port X, then no one else can use output port X, which means that C cannot. But C has a red packet at the front of the queue. There's a green packet behind it, and the green packet is meant for output port Y, which is actually free. So, but unfortunately, C didn't get the use of the output port, right? So this is why like switch design and switching algorithms are very important, because this can really slow down, right? This will mean that this router or this buffer here is filling up. Can potentially fill up and you get packet losses. Okay, good. So the idea is to just give you a flavor for how these routers work. Okay, let's move on. We're going to talk about IP now. IP is the Internet Protocol. It's the addressing mechanism that's used at the network layer. So we already saw there's an addressing mechanism at the link layer, which is what? What was the quote-unquote addressing mechanism used at the link layer? Like, is there any kind of address at the link layer? Yeah? Yeah, there's this MAC address, right? This MAC address is determined by the manufacturer, right? But it's a field in the link layer header. Okay, network layer uses IP addresses. So let's talk about IP protocol here. Okay, so this kind of just shows you where the network layer fits in. So above it is a transport layer, below it is the link layer. Okay, and I mentioned to you that there's a forwarding table, right? Because the router has to do forwarding, and the routing protocol is going to drive that forwarding table. Okay. Now, in addition to these core functions, there's a couple of other things. Well, to be able to build this routing, you need addressing. So IP does that. So IP it deals with addressing, the datagram format, and so on. There's also another protocol called ICMP, Internet Control Message Protocol, and the job of IPMP is just to do error reporting, control messages. Okay. So ping and traceroute fall under ICMP. Okay, you remember on the very first day we met, we did some ping and traceroute. Those are ICMP messages. Okay, here's the anatomy of an IP packet. Okay, again, we're going to do the same thing we did with transport layer. We're going to take data in chunks of 32 bits or 4 bytes, and then stack it on top of each other. Okay? So every row here is 32 bits. Excuse me. Okay, so we have things like header length, the length of the datagram. Type of service is, let me think, hang on. I think this is, yeah, I'm not sure right now. I need to look that up. I can't remember if it's a type of service at the layer above. Okay, it might be at the transport layer. I will look into that. And then like IP version. Right now, this anatomy, this is for IP version 4. Okay. Then there's a second row of header bits, which is for a function called fragmentation and reassembly. Well, so fragmentation and reassembly is not really about finding a route. It's a function that needs to be carried out because a network can limit the size of a datagram. So if a datagram is bigger than that limit, it needs to be broken into smaller datagrams. Okay, so we'll see an example of that later. Then the third set of 16 bits, there's a time to live field. This time to live field is basically a counter, right, that is set to a large value, maybe 50 or 60. And then every time the packet is forwarded by a router, that counter is decremented. Okay, and the reason for this kind of time to live is that you don't want a packet to go in a loop around your network forever. So once it gets to 0, maybe the following router will drop the packet. Okay? What else? There's, upper layer is actually the transport layer. So the type of service in the first row is not the upper layer. It's probably just the type of service on that datagram network. Right? There's a checksum. Then the next two bits are very important, the source IP and the destination IP. Okay? So it's clear why the destination IP should be there, right? Why does the network layer header need to contain the destination IP? Let's make sure we understand why. Yeah, so why is there a destination IP address in the network layer header? I don't know. You're the only one who seems to think so. What about the rest of you? Why do we need the destination IP address? Sorry? Yeah. Yeah, it's not rocket science. But I need you guys to pay attention and respond when I ask a question. So thank you to the few of you. So the rest of you should not just sit back and, this is not a, I don't know, one-way information dump. Okay? Yeah, okay, so why do we need the source IP then? Yeah, so the destination IP, because it needs to know where to go. Why bother with the source IP address? Sorry? Acknowledgement. Okay. That sounds like a good reason. But is there a better reason? Suppose I don't care about acknowledgements. Sorry? Yeah, this is a communication problem, right? A wants to talk to B. Maybe it's asking B for something. B has to send it back. Yeah, that's why it needs to know. That's why the source IP has to be there. When the sender sends it out, it has to put its own address there so that the destination knows who to respond to. Just like when you write a letter, what do? Take an envelope. Imagine an envelope. What's on the front? Sorry? Yeah, you put the address you're sending to, and you put a return address, which is your address. Okay, so again, I think I told you, if I'm going to trick you, I will just tell you. I'll just be upfront and say, this is a tricky question. But these are not, right? Okay, so, yeah. Okay, that's a good question. Well, there's 4 billion of them, right? So the maximum number of IP addresses you can hand out are 4 billion. Are you saying we're above that? Yeah, good, okay. Actually, I agree with you, but your example, that it doesn't come out, right? That's only 7 times, 20%? That's 1.4 billion times 2, that's 2.8. So we're not there yet. Oh, you said 40. Oh, okay. Yeah, then, yeah. Okay, good question. We should be running out, right? Yeah, so that's one of the motivations for IPv6. In IPv6, the address field goes to 128 bits. So 2 to the 128, is that a big number? It's a very big number. I think it's probably something like, I think I looked this up once, the number of atoms in the universe. The number of estimated atoms in the universe. But your question is good. And right now, I can't answer it because we don't understand, at least we haven't talked about it. But it turns out, if you remember when we talked about MAC and IP addresses, when we said, why do we have MAC and IP addresses? One of the questions we asked was, or one of the things we realized was that in a connected network, you need unique IP addresses. In a connected network, you need unique addresses. So what does that mean? What is that hinting at? Yeah, in networks that are not connected together, you can reuse the same IP address. So anyone know of examples of disconnected networks? For example, NUS campus is actually a network that's not connected to the internet. Yeah, it's paradoxical because you're like, I can surf the internet. Yeah, but actually the network itself is not connected. Your home network is not connected. So anything behind a VPN or a firewall is actually not connected to the internet. It creates what's called a private network. And that private network can reuse IP addresses. So, Benita, that's one way we get like reuse of IP addresses. Okay? But we're going to talk about why, if that network is not connected, why does it feel like I'm connected? Right, so we'll discuss that when we talk about something called NAT, Network Address Translation. Yeah, so that's the trick. It's NAT. Okay, what else? Then after the source and destination, we have our data. Okay, good. Are we comfortable with this? Do we understand everything here? Like, at least we understand what the header is, right? Okay. All right, let's talk about this function called fragmentation and reassembly. Okay? And as I mentioned, the idea behind fragmentation and reassembly is that a network operator, the person who owns the network, can put a limit on the size of the network layer packet, the size of the datagram. Okay? And this basically is just a policy that routers can enforce. If a packet is too big, it can drop it. You know, just like sometimes on the highway, it says, if you're a big truck, you cannot get off on this local road because the road is too small. Right? It's only for smaller vehicles. In the same way, the network operator can do that. And what happens is that, so in fragmentation and reassembly, that router that recognizes the big packet, it will actually break it up. So you have a parent packet and you have children packet. Now, the children packet are just regular network layer datagrams. Okay? They're not special. They're just smaller. And then they remain smaller until they get to the destination. The destination that eventually will reassemble everything. Right? So that's where you get fragmentation, maybe at the ingress of a network that has a limit, and reassembly at the final destination. Okay, so in fact, my guess is, if I gave you this problem, that all of you could figure out a scheme to do it, right? Do you think you can or not? Does this sound like a hard problem? Could you guys come up with a way to do this? Yeah? Okay, thank you for being so confident. What about the rest of you? So this is where I want to separate how something is done from, well, I'm going to describe something because, well, we need to have an algorithm. But there's nothing special about the algorithm. You could come up with your own algorithm. So it's more important you understand the idea, and that if you want to do, you could come up with your own scheme. Okay? So it's just a bit of housekeeping, right? So what housekeeping would you need to do here? Like you want to take a cut? Yeah, exactly. The biggest problem is not breaking it up. Breaking it up is easy, right? You need to do reassembly in the correct order. And so for that, you need some housekeeping. So how would you do that? Yeah. So first of all, remember the smaller packets are datagrams. So they have this entire header. But what you're right, that's why this second row is there. This second row is going to be used to do exactly what you're talking about. I mean, this is written here, but you could ignore it for now. Let's assume you have some header bits to do fragmentation and reassembly. So how would you do it? Like, I'm just brainstorm. It's like I said, I think if all of you really just think about it for 10, 15 minutes, you'll be able to write pseudocode for an algorithm. It's really not very complicated. But how might you do it? No. So now, how are we going to do the fragmentation? Well, I'm going to break it up so that my total packet size or datagram size is less than my limit, right? That limit is called the MTU, maximum transmission unit. Okay? So let's say you're going to break it up, but what information do you need? No, that's the MTU, yeah. Yeah, but that's just filling in the rest of the IP. Yeah, but what do you going to need to do for fragmentation and reassembly? Okay, what's packet ID? Yeah, so you assign maybe a packet ID or fragment or a parent packet ID, and then what else? Yeah, and then so fragment number. Yeah, so that could work. So what would I have to do in that case though? Like, if I received all the fragments, then I could put them together, right? So that would work, right? Yeah. Now, if I didn't receive all the fragments, then you could discard the packet. But let's say I don't want to discard the packet. If instead of just telling me the order, can you think of, no, so your solution works. Let's think of a slightly different solution. What else could you do if you didn't want to just look at order of packets? Well, these fragments are kind of like puzzle pieces, right? You got to put them together. So maybe you can keep track of where they're supposed to go instead of the order only. You get what I'm saying? Well, each of the fragments have a certain size, right? So maybe I tell you where it has to go. They have to fit together linearly. Right? So instead of order, I tell you where I know the original packet was this size. I can keep track of where they have to go. Yeah. So I mean, there's a ton of solutions. That's the point I'm trying to make. There are many, many solutions. Okay. So let's look at what exactly is done in IP. Okay. So in IP, so let's say you have a 4,000 byte datagram, but the MTU is 1,500 bytes. Okay. So do we see that? This 4,000 is bigger than this 1,500. Right? And we know that there's 20 bytes of header, right? If you look here, there's 1, 2, 3, 4, 5 rows. Ignore the optional stuff here. So 1, 2, 5 rows. Each row is 4 bytes. So this is 20 bytes. So I have 20 bytes of header, which means that in a 4,000 byte datagram, this is the payload. Right? So it's this payload that I have to break up. Okay? And, well, if you think about it, if the max MTU is 1,500 bytes, that means I have, again, assuming a 20-byte header, for each of the children packets, I'll have 1,480 bytes of payload. And if you work it out, you'll see I need 3 3 packets. 2 is not enough. Okay, and because I need to, for example, know that they're all part of the same packet, I have an ID. Okay, and then I have something called an offset, and this offset is telling you where the packet goes. Right? Maybe offset from 0. Okay, and so that's it. That's fragmentation and reassembly. There's only one maybe perplexing thing here. So if somebody wants to ask me, you can ask me, or we can move on. Oh, that's just telling you whether you're done or not, right? I mean, it's just telling you whether there's any more fragments. Yeah, so let's figure out what the offset should be. So what should the offset of the first packet be? Yeah, for the first child, what should the offset be? Okay, how about the second one? No, what do you think it should be? Sorry? Why should it be 1,500? No, it doesn't. What's the payload for the first packet? Yeah, so what should the offset be? And then what should the offset be for the third packet? What is it? So how much? Yeah, what should the offset be? So I'm a little bit surprised. You told me the offset for the first packet should be 0. The second packet should be 1480. The third packet is now smaller. So the third packet goes before the second packet. You're too busy looking there. You should be thinking. Talk to me. What do you understand? I didn't explain it. So you figured it out? Tell me. It's counted as what? In bytes. Yeah, everything's in bytes here. Why were you? Well, you have figured it out. So have you figured it out or not? Yeah. So this is exactly what I'm saying. So I have this feeling that learning has become, look at the answer, do I understand the answer? That's not learning. No, everybody does this. And actually it's literally, I have to fight you guys to convince you. Getting the answer, looking at it and understanding the answer is maybe 1/3 or at best 1/2 of learning. You got to think through things yourself. Your question is very good. But I don't understand why you look at that and go, oh, okay, I understand because I saw the answer. Maybe my problem is I should remove the answer. So can you do that? Can you think? So tell me again, what should the offset be for the first packet based on your understanding right now? Yeah, so and come up with your own scheme. Forget, I didn't explain any scheme to you yet, right? So like this gentleman did here, come up with the scheme. So what should the offset be for the second packet? Come up with like I told you, you can do fragmentation and reassembly. How would you do it? I'm not asking you, explain what's on here. That's not what I'm asking you. I'm asking you, if you had to do fragmentation and reassembly, how would you do it? How would you set the offset? Yes. Correct, for the second packet. And for the third packet? Yeah, which is what? 1480 times 2. Yeah, good. So you understand fragmentation and reassembly. Yeah. Is everybody get what I'm saying? It's not about explaining an answer. It's about thinking through things yourself. And was that correct? If I give you 10 minutes, you can figure out how to do fragmentation and reassembly, right? Okay, so everybody understand the function and how you might do it? Okay, so now let's see why these numbers are here, why IPv4 does this. Okay, so if in your example that was shown here, what's the range of the offset? It can be from 0 up to 1480, right? And how many bits do you need to represent that? Does anyone know? If I want to represent something from 0 to m, how many bits do I need? Sorry? Log 2m? Why? Well, what? But why log 2m? But why is log 2m? Why isn't it just log m? Yeah, log m bits, right? Yeah, so let's say, but if I want to represent something between 0 and m, that means my offset can be any value between 0 and m, right? That means I can break this packet at anywhere I want, any byte boundary, okay? So, but I need log m bits. Let's say I don't have log m bits. Let's say I have less. Can you think of a way to reduce the number of bits I need? Well, how about we don't allow breaking at arbitrary byte boundaries? We allow breaking, suppose, only at 2 byte boundaries. Then if I allow breaking only at 2 byte boundaries, then what's my offset? Is it still 0 to m? It's not, right? What's my new range of my offset? Yeah. And how many bits do I need for that? One less bit. No, one less bit. Log m, now I need log m by 2. What's log m by 2? It's log m minus log 2, which is log m minus 1. So I need one less bit. So that's how you can reduce the number of bits you need, by allowing the breaking to happen on some, some bigger chunk. So in this example here, I'm dividing by 8. So what am I allowing only? I'm allowing this to only break on 8 byte boundaries, which is why my offset now will go from 0 to 1480 by 8. So I need less bits. In this case, I will need 3 less bits. Right? Yeah, so that's the reason for dividing by 8. Yeah. Yeah, I mean, one could do that. I mean, like I said, this is not like the Word of God. This scheme is there because there needs to be a scheme. Yeah, that's why in this class we're always questioning, right? We're always asking, why was that done that way? Why was that done that way? Yeah, because what you'll find is that sometimes things are done for a reason. Sometimes things are done because something needs to be done. Yeah, seriously. No, you don't get to choose this. The protocol. And anyway, the user doesn't interfere. It's the network operator, right? Yeah, then you have to have some. So this is obviously going to restrict how you break it, right? That means you might have some empty space. The bigger you make the boundary on which you break, the less efficient you might be, right? When you break on byte boundaries, you can fill up the whole packet. Right? If I break it up in, let's say, 2-byte boundaries and there's an odd number of packets, you know that one of the packets is going to have an empty byte. Yeah, I mean, that's the price you pay. It's an engineering problem. But good question, thank you. Okay, are we good? But do you see my point? Let's work on thinking and less on, because everybody is, it's not you guys, but in my previous experience, everyone asked for, well, can I get the solutions to this? Can I get the solutions to that? But actually, to me, that would get in the way of you learning. A little bit of struggle is actually good. You know, struggling is not bad. Struggling is equal to learning. Okay, so keep that in mind. Okay, are we good on this? Yeah. Yeah. But it's only done at the destination. Remember, it's not done by intermediate routers. I think the problem you're talking about, what would happen at intermediate routers? Okay. No, the packet is not too big because it overflows the buffer. The packet is too big because the network has set a maximum transmission unit. Yeah. I don't know what you mean by every single piece arrives. But but there's no 8 anymore. I'm not sure what you mean. It's already been broken up. Now there's three children packets. Yeah, so. None of them can be processed until all of them are. Okay. And so wouldn't they just sit in the buffer? Mm-hmm. Okay, and what's the problem? They're small packets, right? What it's too big? There's no it anymore. They're small now. Yeah. Yeah, but this is at the destination. It's at the destination, because the destination is the one that interprets the data. Yeah, I mean, you can have lots of policy. You can say, I'm going to, if it doesn't come on a certain time, I'll just reconstruct what I have and ignore the rest. But the application can make that decision. Like if this is streaming video, for example, it might be just part of the video. In any case, if it's real time, if something's delayed, it's of no use, right? So, but the point is that it's not going to affect the intermediate nodes, which are going to run routing. But the end destination can have intelligence. And I'm not saying anything about what the end node does. The end node can do whatever it wants to do. You, as the application writer, get to decide that. Does that make sense? It's fragmentation and reassembly does not say what the end node does. All it says is the end node must reassemble. It doesn't constrain the end node in any way. Okay, good. Anyone else? Yeah, Benina, you had a question? Yeah. Yeah. usually in this example, don't have 2 big packets and a small packet. Have 3 equally sized packets. Yeah, why not? You could do that. I don't know. Yeah. Yeah. Yeah, because you need to make a decision, right? You need to have a protocol. Protocol has to be a very specific set of rules. So yes. But what you described is not infeasible. If you wanted to make that your rule, you could. But I don't see any benefit in that. What do you mean? But it might not fill up the whole packet. It depends on the original packet size, right? In this example, maybe, but otherwise it might not. No, even the first packet cannot be. Because if this was instead of 4,000 bytes, if it was 3960, for example, or 3970, 3970 in this example is not divisible by 8. So you won't fill up the first packet, right? You can't. No, you can't because you're limiting the offset. So you didn't get that. I'm not breaking it up on byte boundaries. Breaking up on 8 byte boundaries. I mean, in this example, yeah. So you might not fill it up. Let's say there was an odd number of packets. Then how are you going to fill it up? You can't, right? Yeah. It's set by the network operator. Yeah. So it's not up to you, the user, or the network, or the packet. It's the person who owns the network. Yeah. Okay, good? All right, good. So, okay, let's move on to addressing. Okay, so this function is done. We never need to come back to it because it's not part of addressing or routing, but it's implemented at the network layer. So we'll move on to what actually affects the network layer, which is addressing. So we've already talked about this. IP addresses are 32-bit quantities, and what we normally do is we break them up into 4 chunks of 8 bits each, or 4 bytes. And then we take those bytes, those 8 bytes, those 8 bits per byte, we take those 8 bits, and we represent it as an integer from 0 to 255. And that gives us the so-called dotted decimal notation. So this IP address is 223.1.1.1. Okay? The other thing is that every interface requires an IP address. So this router, for example, has 3 network interfaces. So each network interface has an IP address. Okay? So there's one router here, there's 3 interfaces, and so this router has 3 IP addresses. Now if you look at all of the IP addresses, for example, on this interface, do you see something common about them all? What's common? Sorry? The .2 is common. Is that it? The 223 is not common? So I asked you what's common about the IP addresses. Yeah, the first 3 numbers. 223.1.2.x. Right? All the IP addresses are of this form. Okay? How about this one? This is 223.1.3, right? And this is .3.x, right? So you could already see the structure, okay? So now, not surprisingly, that 223.1.2, you could almost think of it as the ID of this network, or we call it a subnetwork, or a subnet, okay? Okay, yeah, so the IP address is going to have a subnet part, and it's going to have a host part. So we see what's different about these guys here is this last byte. So this part here is a subnet part, and this is the host. Okay, so a subnet, if you look at this, is just any interface of a router. So if you have a router, and it has an interface, that interface defines a subnet. So how many subnets are here? Right, 3, because this router has 3 interfaces. Okay? What about here? Oh, yeah, so we already saw, yeah, this is the one with 3 interfaces. And what we're going to do is, there's going to be a little naming convention. So I mentioned to you this 223.1.1 is kind of like an identifier for a subnet, right? So when we want to do that, in addition to saying 223.1.1, we also need to say how many bits are in the subnet part. Okay? Because now, if you could only make subnets on byte boundaries, then you wouldn't need that. Saying 223.1.1 is enough. But your subnet part can be any number of bits. It doesn't have to be a multiple of 8. Okay? So this is why you need to specify this 24 here. And this 24 here is what's called the subnet part or the subnet mask. Okay? So in this 3 subnet network, we have a 223.1.1 subnet, 223.1.2 subnet, and 223.1.3 subnet. Okay? So this is just some terminology. Okay, everybody good with this? Yeah? Then tell me how many subnets are here? Okay, so someone said 3. Okay. Anyone else? Do we want to go for 4? 5? What do you think? Yeah, you. Oh, he said 3, okay. Anyone else? What do you think? Yeah. So here's a trick. This works without fail. If I point at you and you like turn around, it's you. So if you feel the need to ask, is it me? The answer should be yes. So you say 6. Okay? Do you want to explain why? It actually is 6. But why is it 6? It's not 3, it's 6. Why? Can you tell me? Yeah, exactly. So you have a subnet here, then and subnet here. But remember that these routers have other interfaces, right? You have this interface, but this interface is connected to this interface. So this is one subnet, and then you have one subnet here, and one subnet here. Okay? Now you might think, but there's no computer here. There are two interfaces on that subnet. Right? If you wanted to, you could hang another computer off there. Okay, so remember, every interface of every router creates a subnet. And that's what differentiates a router from a switch. Okay? The interface of a switch does not create a subnet. The interface of a hub does not create a subnet. The interface of a router creates a subnet. And you need to do routing. Okay, so hub was a layer 2 device, and all of the ports on a hub are connected. Now a switch is a layer 2 device, but all of the ports of a switch are not connected. But it's still a layer 2 device. All of it is still the same subnet. No routing. Every time you have a subnet, you have to do routing. Okay? And a router is reserved for devices that create subnets. Right? So sometimes it's a little bit confusing because people talk about layer 3 switches. A layer 3 switch is a router. So sometimes it's just marketing. But the easiest way to imagine is you have 2 layer 2 devices, hubs and switches, and you have 1 layer 3 device called a router. Okay? And every interface of every router creates a subnet. And therefore, you need to do routing. Now, the switch is an interesting object. The ports are not connected. But you still need to figure out which node is available from which port. Now, you studied that, right? How is that done? How does the switch know? Because the switch is not a hub, right? A hub, when it transmits on all its ports. But a switch doesn't. So what does a switch do? Or what does a switch have to do? A bit louder? Yeah, or just, you're correct, but maybe that's a mechanism. But what's the function it has to do? It has to keep track of which devices are available on which port. And there's many ways of doing that. But it has to keep track of it. Okay, maybe it has to learn it has to figure it out, but then it has to, but this is different from routing. It's different from the forwarding table at the network layer. It's another mechanism at the link layer. It's an extra thing the switch has to do. Okay? Yeah. Routers don't do that. I said the routing algorithm. Yeah. It can if your routing algorithm takes that into account, yes. But probably the first level is connectivity. Right? If a certain router goes offline, then your network topology changes. And the network topology, if you're doing centralized routing, you have to know that change. If you're doing non-centralized routing, if you're doing distributed routing, perhaps you can adapt to it because it's a local thing. It's a local event. But yeah, so as the topology changes, you have to keep track of it. Yeah, and you could bring in things like congestion as well. Okay, good? So we understand what's a subnet. Okay, so this is the generalization. Okay, it's called classless inter-domain routing. And in classless inter-domain routing, this is just a way of specifying subnets and hosts, right? So you have this 32-bit address here. And there's going to be a subnet part here. Okay, in this case, the subnet part is 23 bits. and there's going to be a host part. In this case, the host part is 9 bits. Okay? So we see that this subnet will be identified like this. It's the 202.23.16.0/23. So all the parts that are not in the subnet part are zeroed out when we want to specify the subnet. Okay, so everybody good here? So the reason we talk about classless interdomain routing is in the early days of the internet, subnets could only be like size 8, 16, or 24. You had class ABC networks. Okay, and that was easier in the past because, well, computing hadn't advanced so much, right? It was a little bit more difficult to do things like this. But these days, computing has advanced. We have enough memory. Routers are fast. So we basically allow the subnet part to be anything from 0 to, well, from can be from 0 to 31. Okay? Let's see. Okay, let's ask a couple of questions. In the 20, so this is 200.23.16/23 subnet. In this subnet, how many hosts are there? Well, there are 9 bits in the host part. So how many hosts can this network support, this subnet? Yeah, correct. There's 2 to the 9, because there are 9 bits in the host part. There are 2 to the 9, let's say, addresses. Okay? But the all 0 and the all 1s, these two are not used. They're not assigned to any host. So if you want to be technical, say how many hosts can this network provide? It would be 2 to the 9 minus 2 hosts. Okay? The all 0 is not assigned to any device because it's the network ID. Right? I told you this when it's all 0, you give it a special status. Does anyone know what the all 1s is used for? If I did the IP address would be this. So yes. Suppose I take this part here. Yeah. Suppose I was here. So I have the subnet part is the subnet part. The last 9 bits are all 1s. That's what I mean by all 1s. Yeah. So this one, subnet ID, and this one is the broadcast address. Okay? What we mean by broadcast address is when you want to send to every node in the network, this is the address that you use. Okay? So these 2 addresses are not used to assign to any host. All right, good? So that's this. So we saw we saw how many hosts there are. There's a subnet. There's a subnet part. We saw what the broadcast address looks like. Okay. Now, in Windows TCP/IP settings, there's something called subnet mask. Right. I called this 23 as a subnet mask. right? But what that actually means is when you set the subnet part to all ones, then that becomes a mask, because then you can, from an IP address, you can figure out what the subnet mask is by just doing what? By just doing an AND, right? Yeah. If you do an AND with the subnet mask, you extract out what's the subnet part. So I think Linux and Mac don't use this, but I think in TCP/IP in Windows, there's this number here, which is kind of like all one. So you would do like, in this case, you'd be like 1111 dot. Now I've got to go 1, 2, 3, 4, 5, 6, 7, 8. This is sometimes in Windows also called the subnet mask. Okay, so it would be 255.255.254.0. Okay, good. So do we understand CIDR? Okay. Okay, so how do you get IP addresses? Like, how does a device or an interface get an IP address? Well, actually, you might not know this, but you can assign it. You can go into the settings and you can assign it. But typically, we get IP addresses in an automatic, in an automatic fashion using something called DHCP. Okay, so again, DHCP stands for Dynamic Host Configuration Protocol. The idea is that a device comes to a network and says, hi, I want to join your network, right? Maybe there's some authentication. You got to figure that out. But once that's done, the network assigns that device an IP address. Okay, and that's DHCP. Now, we can talk about the DHCP protocol, but again, I think if I leave you to think about it for 10, 15 minutes, you could come up with a workable protocol. So there's, again, nothing special about the DHCP protocol. It's just a way of the network authenticating a user and then assigning it an IP address. I say, okay, on my network, you use this IP address. Okay? So it's kind of like, so typically in a network, there's going to be one of the computers on the network is going to be the so-called DHCP server. And often, this is your router. Your router can serve as the DHCP server. Then a new network comes in, a new node comes in. That new node is going to send a broadcast message to everybody in the network. Says, hi, I would like an IP address. Of course, because it's a broadcast message, the DHCP server will get that message. It will respond to it. And so the question, how is authentication done? Sometimes authentication is done by MAC address filtering. So the DHCP server has a set of predetermined MAC addresses that it will allow. Okay, so for example, NUS does that. When you want to assign fixed IP addresses, you need to give NUS the MAC address of the computer that's going to connect to it, plus the network point. Only then will they give you a fixed IP address. Otherwise, it won't. Right? Otherwise, if you connect it, it will give you a dynamic IP address. Sometimes when you go to, for example, to a mall, you want to connect to wireless at SGX, or you want to connect to airport Wi-Fi, well, you have to authenticate, right? There's a landing page in which you have to type some code or some account, right? So that's another way that authentication can be done. And as I said, the protocol is not really all that important. You can figure it out, right? So the arriving client will send, so you notice that the destination here is 255.255.255.255. That's the broadcast address, because the arriving client doesn't even know the subnet, right? So it's going to have to just set everything to all ones and send the packet. Okay? And then there's a back and forth, and eventually the client will get an IP address. Okay, so that's the typical use case of how devices get IP addresses in a network. But how does the network get the IP address? Typically, it gets it from an ISP. Okay, so for example, so this is where we're really going to see the hierarchical nature of IP addresses, right? So I'm an organization. I have 23 address, right? So I'm organization 0. Let's say NUS is organization 0, right? It has a /23 address, meaning each subnet part is /23. So where did it get it from? Well, we get our connectivity from Singtel. So Singtel, or the network operator or the ISP, could have a /20 range of addresses. So notice /20, which means it has more addresses, right? Because it has 2 to the 12, right? And what this ISP can do is it can break up its 2 to the 12th addresses, okay, into 8 blocks of 2 to the 9, or 8 /23 addresses. Why 8? Because 23 minus 20 is 3. So there's 3 bits that are used to identify the subnet. Right? There's 8 subnets. So 2 to the 3 is 8. And so the ISP will give the organization, oh, here is your /23 range of addresses. Okay, and this is an example here. So notice that this seems to look the same as this, but it's not because of this. Okay, the 2 subnets are different. They have different IDs. Okay, then, maybe a little bit about how this helps you, right? This way of assigning addresses is very helpful because if somebody wants a route to organization 0, they only need to know the subnet ID of organization 0, which is these first 23 bits, right? So for example, all these organizations, they're going to be, let's say, so this is my ISP here, okay? This is the same ISP as here, okay? And so remember, the range of addresses for this ISP is this /20, right? So the ISP just has to advertise to the rest of the internet. Anything that looks like this, where the first 20 bits match this, send to me. Right? So the internet doesn't have to keep track of all the hosts. It just has to keep the subnet ID of this ISP. Now, you could also have, so this was my original ISP. If, for example, organization 1 wants to have a more specific route, it can do that through another ISP. It just has to keep track of or advertise the /23 route. Right? You see that, right? So the original ISP just has to advertise the /20 route. If I want a more specific route to one of the organizations, it can advertise a longer prefix. And what do routers do? This is in the beginning. How do routers decide which interface to forward on? Longest prefix matching, right? So, because this is going to advertise the /23 route, this will win for organization 1. Okay, so routers here will have both that and the /23 route. And it will match the /23 route and give you the more specific route. Okay, we'll see later that this leads to, this is very efficient and very useful, but it can lead to big problems. So I'll show you an example later when we talk about some real world consequences of networking where YouTube was taken down. Meaning someone decided to advertise a more specific route to YouTube because they wanted to block YouTube. And a country can do that. Like I could be in country X and we could be in Singapore. And Singapore could decide to block YouTube. Right? So how would they block YouTube within Singapore? They would advertise a more specific route that covered the YouTube address space. Then all your packets would go to, /dev/null somewhere. Okay? Now, that's not illegal, right? Like, if a government wanted to do that, they could. What happened in the other scenario that I'll tell you later is that advertisement got leaked to the rest of the world. And for about 8 hours, YouTube went down. Okay, so the last word on this is, so we see that a device gets it from the DHCP server, from the network gets it from the ISP. Where does ISP get it from? The ISP gets it from this organization called ICANN. Okay, ICANN is also the body that handles domain name services. So for example, if you wanted to register your www.friendlyname.com, your registrar has to go through ICANN. Okay, so there's this world body that handles domain name, but it also handles assignment of IP addresses. Okay, so I think that's all I want to say about addressing. Are there any questions? There's no default value. You're talking about the, what? You have to, actually. You're talking about the subnet mask, right? Yeah, you have to. There's no default value. You don't need to put it for a host. But if you want to specify a subnet, you do. For the network interface, it doesn't matter. Because routing is done by longest prefix matching. The forwarding table already has the prefixes. Right? Remember, if you go back to here, this right here, this is my router. This is the forwarding table in my router. So the router already has all the prefixes, right? So, but when a destination comes in, I don't need to know anything about subnet or host. I just need to match this to this. So when you want to specify a subnet, you need to know how many bits in the subnet. And you can do that by just specifying the prefix, right? If I tell you the first row, that's a prefix of a subnet. Because you know how many bits are. That's less than 32. All the rest of the bits are 0. I could turn that into a dotted decimal notation. If I do that, then I have to tell you how many bits in the subnet. Yeah, good question. Thank you. Anyone else? So we understand IP addressing a bit more, right? And where this hierarchical structure comes from. Okay? So the one thing, we'll do some examples of this later, but the example I gave you was when we had Singtel or the ISP. This one. We saw that the ISP broke up its range into smaller ranges. okay? But sometimes we also want to say, given a set of ranges, what's the aggregation? Like, for example, if I gave you these 8 addresses, and I asked you, what's the aggregation of those addresses? That's like going from here to there. Okay, and you can do it either way, right? Breaking it up is easy, and aggregation is not that difficult. You just need to look at the ranges and find the common prefix, right? If you looked at those 8 sets of addresses and you look for the common prefix, you see that there's 20 bits in common, and those 20 bits are the aggregation, right? Okay, good. Okay, we'll do some examples of this. Yeah. Okay, if there are no more questions, let's end today. We've gotten to a good stopping point. The stopping point is NAT. Network, address, translation. And Benita, this will answer some of your questions about how we're able to function without running out of IP addresses. NAT helps a lot. Okay, thanks. I'll see you all on Wednesday. And if you have questions, I can stick around for a while. Yeah. Yeah. The question was this one, right? Yeah, this has 6 subnets because, so the way to determine this is to look at every interface of every router. So what you can do is this. You can break every interface, okay, and then see how many islands are left. So when you break this interface there, oops, sorry. Yeah, no, yeah, the things connected to the router. You break them. And when you break them, you're left with this island, and this island, but you're also left with this island, and this island. That's why there's 6. So you're asking why is this a subnet? Yeah, but there's 2 network interfaces at that connection, right? There's the router 1 and the other router. Yeah. Yeah. Yeah, but it's only true if it is a router. Right? If it's a switch, those connections are not subnets. Yeah. Okay, thanks.